So let's now move on to the one norm. So in order to develop the proximal map method, we will need to know what is the subdifferential for the one norm. What does it look like? And then that will make life much easier once we get to the proximal map solution. So in our case, or in the case of the one norm, our function f of theta is now this one norm, which is what is the sum of the absolute values of the components of theta. So let's define a point theta star like this. Its components are theta 1 to theta p with stars as superscripts, and it's a column vector. Now, for any theta star such that the jth component is greater than 0, what's the partial derivative with respect to this theta j, right? Which is greater than 0. So let me just back up a bit here. What I was saying was, why are we doing this? Well, we want to know the gradient of our function or subgradient at some point theta star. What is the gradient? Well, the gradient is the vector, covector, vector of all partial derivatives. Now, because of the form of the one norm, it's given by this sum of, let me just write it out actually. It's given by this sum, theta 1 absolute value plus theta 2 absolute value all the way up to theta p absolute value. If we take the partial derivative of this with respect to some theta I, or theta j here, what's going to happen? So the partial derivative of this sum, well, one of these is theta I, right? The rest don't depend on theta I. So their partial derivatives with respect to theta j are 0. And so what's going to end up happening, if theta j is greater than 0, we'll just get plus 1. And if it's less than 0, we'll just get minus 1. The only problem that we'll have is if one of these is 0, the one that we're taking this partial derivative with respect to. So as long as theta j star, the point where we want to find the gradient or subgradient, is either positive or negative, the subgradient is unique and it's either 1 or minus 1. Minus 1 in that case, plus 1 in that case. Okay. So now what? So in those cases where none of the components are 0, none of them, we can write the subgradient as uniquely this thing here. It's just the sign of each of the individual coefficients. And what's this sign function? It's plus 1 if its argument is positive, and it's minus 1 if its argument is negative. So if theta 1 star is positive, this is just plus 1. And if it's negative, it's minus 1. Right? So each of these components, theta 1 star to theta p star, is either positive or negative. So what we'll end up with is a vector of plus ones and minus ones. Right? And that is the subdifferential. It's a singleton set which contains just this one vector. This point, theta 1 star up to theta p star, where none of them are 0. Right? None of them are 0. They're either positive or negative values. In that case, we have a unique subgradient, which is just the gradient of the norm. Right? So the problem will obviously come in when one of these theta stars components is 0. So what will happen in that case? So let's say that we have this component, the jth component, is 0. And in that case, the subgradients V star will have jth component taking values, as we've already seen, between -1 and 1, right? Because the partial derivative in that case, d by d theta j, doesn't exist. But what does exist is a subgradient, in fact, a whole set of subgradients, right? And that set of subgradients, V star, we call them Vj star, will be all numbers between -1 and +1. Right? So if the jth component is 0 of our theta star, this theta star here, then what we have for that jth component, in lieu of a derivative, is a set of subgradients, any value between -1 and 1. And so the gradient will be the rest of them, if they're positive or negative, just these, and then we'll have one component which can take any value between -1 and 1. And so we'll have a whole range of subgradients. All those vectors such that the jth component is any number between -1 and +1. So the subdifferential at a general point will then look like this. So let me explain this. So now we're picking a general point, theta star equals theta 1 star. Let's say the jth one is theta j star up to theta p star. Right now, if one of these is positive or negative, in other words, not equal to 0, then the component of the subgradient will be equal to the sign of that component, which is +1 or -1. In other words, the derivative, the ordinary derivative. Well, not ordinary derivative, the partial derivative, which will give us +1 or -1. On the other hand, if the component is 0, then the jth component of our V star, our subgradient, will be any number between -1 and 1. So what we're going to end up with is vectors that look like, let's say the first one is 0. Let's say theta 1 star equals 0, and let's say theta 3 star equals 0. What we'll have is all the rest, and let's say there are 5 of them, or let's say there are 4 of them. So it's theta 1, theta 2, theta 3, and theta 4. So the first one is just going to be, so let's say we have theta 1, theta 2 star, theta 1 star is 0. Theta 2 star, let's say that's 1 or 2. So it's a positive value. And let's say theta 4 star is -3. Right? So the second, first, second, third, and fourth, the last one is going to be -1 because -3 is negative. The second one is positive, so that's going to be +1. And here, any number between -1 and 1. And here, any number between -1 and 1. So for example, we can pick 0 here and 1 here. And then this 1, 1, and -1 is a valid subgradient. Right? Now we can also pick 1 here and 0 here. So this 1, 1, 0, -1 is also a valid subgradient. And all those vectors that we can generate where this is any number between -1 and 1, and this is any number between -1 and 1, is a valid subgradient. And so that's what this is saying. And that's exactly what this is saying. We have a whole set of these subgradients, and together they form the subdifferential. Now, if they're all 0, then what we have is this product space here. So basically, we have any vector that lies in, so any V star that lies in this space minus 1 to 1 times this Cartesian product minus 1 to 1 times dot dot times minus 1 to 1. And what does that mean? Well, it's any tuple. We can think of it as a vector. It's isometrically isomorphic to 1. Any number, so this is any number in here, let's call it v star 1, and then v star 2 is any number in here, so this is any number in here, this is any number in here, and the third one will be any number in the third one, and so on and so forth, and this, the p star, will be any number in minus 1 to 1. So that's what this means. So that's the extreme case where all of the components are 0.